with a student called Anup Deoras, who's a PhD student at Johns Hopkins University. I don't know how to use this, but maybe everything is going to work out all right. So it has to do with speech recognition, and this is the usual setup of speech recognition, and this is the usual formula. And the only thing that's different that we admit to right here is that there is that parameter mu, which balances between the acoustic model and the language model. And it has nothing to do with our with this lecture. It just is there because that's how it's done. So normally, before that, so in order to carry out this procedure, the speech recognition, we need to have two models. This is called the acoustic model, which tells us what the signal is going to be given that we have some sequence of words that we want to pronounce, and this is the a priori probability that the words will be pronounced. And the machinery which establishes what this probability should be is called the language model. So here, the language model would by base criterion be written like this. Here we're taking the view that the utterance has m different words, and but in reality that to get this kind of probability with all this long memory would be prohibitive, so we put the past into an equivalence class. In reality, most speech recognizers have so-called have a so-called n-gram language model, which means that the equivalence classification has to do with n-1 last words just before the word that's to be predicted emerges. And there are two parameters. There is how long the memory is or the history is, and that's n. And on the basis of how many, how large a training data is this probability estimated. Okay. Now, speech recognition is an inaccurate art, and we don't really know, even though one can come up with the most likely output, modern systems give a choice and allow what we call rescoring. In other words, there is some kind of a set of words or utterances which the recognizer thinks might very well be might be one of those that was really spoken, and then an opportunity is given to a better language model and better acoustic model to see to select from among them. One cannot use those better language models and better acoustic models right from the start because they are too complex. So what's normally done is that there are some relatively simple language models and acoustic models which are used in the first instance, and then what is derived at the output of the recognizer is the so-called lattice. I keep making mistakes like here. And this lattice, as you see, consists of links, and these links correspond to possible words, and any path through this lattice is, from the point of view of the rescoring, a possible sentence. And this is a compact kind of a way to list all the possible sentences that we are going to consider and that we are going to rescore. And what you see is that we have these words here, and also we have a timing. And so that means that, for instance, this you word should occur between this point and this point in time, and so the signal, speech signal that exists between here and there is the speech signal which accounts for the U. Here there are no disputes. It's either it's U in all three cases, but here, for instance, the word between 0.08 and 0.09 can be either how or it can be now. Anyway, the task here now is to come up with rescoring, namely to figure out now, have a second chance which path through this network might be the most likely one from a point of view of more sophisticated models. Another thing that I want to say, stress here is that this is a lattice from the point of view of a bigram language model, meaning where the n is equal to 2. It turns out that the lattices from the point of view of a trigram language model, which is more useful, would look like this. And so they would be much more complicated. And the reason that we have to make this adjustment is so that the word being predicted, which is, for instance, U, should depend on two previous words, and they may be different. Here the two previous words are how are, and here are now are. And so in the first place, one does not generate a bigram language model, bigram lattice. One generates a trigram lattice. One does not generate a trigram language lattice. One generates a bigram lattice, and then one adjusts the lattice in the way in which I'm showing it here. Okay. So if you want to use a complicated language model, for instance, one that has to do with grammar, then what you really need is to not have these choices, but you really need to have a list of possible sentences, meaning the list of possible paths through the lattice, which will give you the totality of the possible sentences. But the number of these sentences is enormous. So here, for instance, one path is hello, how are you all today? And then there is another sentence, hello, now are you all today, etc. And if you use a complex language model, then you have to do it from an n-best list, which is derived from the lattice. However, there is a way to simplify the lattice into a so-called confusion network. And that's the work of somebody named Lydia Mangu, who's now at IBM and used to be our student also at Johns Hopkins. And what you see here is that what happens is that the lattice is reduced into what's known as confusion network, which is more or less equivalent, and the paths it's equivalent, and it's much simpler, because what it shows you is what the alternatives are. Here it's not clear what the alternatives are in time. Here it's either hello or well, or there is the word oh or nothing, or there is the word oh or now or oh, etc. So there is a technique by which you reduce the lattice into this confusion network. And then your task of rescoring is to choose among these alternatives. Okay. And the most probable path that we had before in this particular case, from the point of view of the original models, is the one that I'm indicating here. And the question is, can we come up with something better? And so we want to rescore this by a better language model. but complex language model need one history at a time. I've said it already. So the question is how to apply this more complex language model while still retaining the formulation of the confusion network. So here I have done it again, except that I've written the alternatives in such a way that the alternative that seems to be preferred is the one having to do with the lower branch always. And the iterative decoding that the title of the talk refers to has to do with what I show you here. It will try to choose among the alternatives one at a time. So it will start out by pretending that it's already clear what the rest of the choice is. So there is only one path, but displays a particular choice at one link only. So here we would, with this as context, we would want to choose between well and hello, and we would want to choose it as a, in other words, we would like to find out what's the probability of this sentence which is the path with well, and what's the probability of this sentence, which is the path with hello. And it should be a function both of the language model and of the acoustics. So it turned out that well was less probable than hello, and so the two alternatives are switched, and the currently best alternative is again the lowest path. And this continues. So next we have an alternative between O and nothing, and well, I don't know, and it's chosen O happens to be better, and so this is temporarily the situation, and eventually we proceed from left to right, and eventually we get to the last choice, and the choice is between day and end of sentence, and it turns out that end of sentence seems to be the best, and we are going to keep iterating it one after another. All right, so the next this is supposed to indicate that I'm going from left to right, and that I always decide first on the first, not decide permanently, but temporarily decide on the first alternative, and then when I choose it on the second alternatives, etc. Turns out that in our case we only do three iterations. It turns out that everything converges, which means that after the third iteration, if you try to do this iterative decoding again, and that means if you want to choose between well and hello with this as temporarily sure context, and then if you want to choose between O and nothing, etc., then nothing changes, everything stays the same, and once everything stays the same, that's your decoding. All right, so in this particular toy example, it turns out that the best sentence of the iterative decoding is the sentence, hello, how are you today? So that's the end of iterative decoding, the way, the most primitive way, which is what I'm talking about here. And you may then ask what the results are. Well, it turns out that that the error rate is improved. By baseline, we mean if we took into account a very large n size, in other words, a list of alternative sentences that is very large. I think in the next slide there's going to be. It turns out that the amount of work that you have to do to compare this list and achieve the result that I am showing over here is 11 times higher or larger than what iterative decoding gives you. The problem that of this primitive way of doing iterative decoding is that it's a greedy search, and what we want to do in the future is to not be so greedy, overcome the greediness of iterative decoding by using something called simulated annealing, then use a much better and more complex language models, for instance, those that are based on neural networks. We had a student named Thomas. I'm sorry, people from Brno should help me. Who Morozov is his name? Mikulov, who visited, pardon? Mikolov. Tomáš Mikolov was recently for half a year at Johns Hopkins and developed an excellent neural network language model, which requires what I've talked about. I mean, it requires this unique context. And so we are going to apply that to the problem, and then another way of improving it so that we don't make decisions immediately has to do with formulating the problem as minimum base risk rescoring. That's the end of my talk. Thank you very much. If there are any... If there are any questions, I'll be glad to answer them. No? Okay. Well, thank you.